This is going to explain to you what it actually see. Let's go. Good afternoon, ladies and gentlemen, and welcome to our talk, and welcome also to our Zoom friends who are watching from afar. It's a great pleasure to introduce John to you. John is an engineer by background who worked on weapons systems. I first met him because he runs something for U3A called STARS, Science, Technology and Related Subjects. And the first experiment he did when I was there was what's called the thin slit experiment. You shine light through a thin slit. But what it does is it shows both the impact of the theory of wave motion and also the theory of particle motion in the same experiment. And I never understood that at university. So to see it actually operated on was really something rather special. So John is an engineer, as I said earlier, and so we're looking forward to hearing about the Space Telescope.
Thank you very much, Hamish. Thank you very much, Hamish. Just to give you a little bit extra background, I was always a jack of all trades. I was somebody who actually knew nothing about everything, and I worked with a lot of people that knew everything about nothing. In other words, I was a generalist working amongst specialists. So that's my background. So if you ask me any very difficult questions, I shall be stumped. So we'll see how it goes. To carry on also, that this is not a presentation that will show you lots of James Webb Telescope pictures. They're coming in at such a rate now, you get a different one every day. You can look them all up on the net. What we hope to do here is to show you how we arrived at the James Webb Telescope, going back from first principles all the way through the progressions that occurred to get there. It's another point that hopefully you'll understand at the end of the presentation. Many of the pictures that you see in front of you of the James Webb Telescope, the publicity pictures, they are artist's impression, and 90% of them are wrong. I don't know, perhaps you can see from this picture why it's wrong, but at the end of the presentation, you will certainly understand why it's wrong. So we'll press on. Now, we did say that we'd start off with the Hubble telescope images, which actually show you one of the deepest parts of space that was seen by Hubble. This is that particular image, or one of the images, and you can see marked on the presentation here various coloured squares. They're very difficult to see, but you can see them as little diamonds on the wrong one. Sorry, little diamonds on the presentation here on the picture, and at the top, of course, are those diamonds expanded up, and you can see you're pretty much at the limit of the imaging here because you see all the pixels lighting up. But you can see amongst those pixels these bigger images, and these represent galaxies that are a very long way away. The higher the Z number, the further away they are. And we'll start off progressing now and see how we got there. So the talk effectively is going to cover 10 or 11 major points. And we start off with, mankind's early understanding of the universe and heavens, the telescope and nebula, bigger telescopes and galaxies, measuring the distances to galaxies, measuring the movement of the galaxies. And then we bring in the astronomer Edwin Hubble, of which the Hubble telescope was named after, and the expanding universe. We then have the emergence of infrared astronomy, space-based infrared astronomy. We then start looking at the precursor telescopes to the James Webb Space Telescope, And we finally get to the James Webb Telescope and some pictures for discussion at the end. We'll cover these areas. Of course, we'll look at mankind's first instruments. We'll look at the telescope, the spectroscope and the Doppler effect we'll be looking at, nebulae galaxies, and parsecs, standard candles and Cepheid variables, redshift in the expanding universe, photodetectors and light integration, force color imagery, the Lagrangian points and halo or light gas orbits. And if we cover all those bits, we've got everything that we need to know about the James Webb Telescope, hopefully. So if we look at mankind's earliest views of the heavens, he noticed that there were the sun and the moon, obviously, and the fixed stars, and they seem to move around the galaxy, around the sky very slowly. And these motions gave us our first motions of time, days, months, years. Planets effectively were bright stars that appeared to move across the heavens, and they were known as wandering stars initially. I think the word planets comes from the Greek, from wandering stars. And of course, all of these were seen by the naked eye. There wasn't any assistance for that. And a lot of mapping of the celestial sphere was done. You see the fixed background of stars here, and mankind, it superimposed patterns upon those fixed stars, and we still use those patterns today. And of course, mankind's first instruments were actually made to measure those things. You measured the points at which the celestial bodies crossed the horizon, or you measured the angles of elevation to those celestial bodies. And these are examples of our first instruments. Instrument making, I think, was the next step beyond tool making, which sort of started to elevate mankind more above the animals than tool making did, as many animals do make tools. Now, the next big step was the telescope. This was the first thing that gave added perception to the eye and enabled these things in the sky to be understood. And it enabled images of the sun, the moon, and the planets to be seen. But also, when looking at the fixed stars, a number of fuzzy objects were seen which moved around with the fixed stars. These were called nebulae. If I use this picture here, it's a classic illustration of perspective used by artists and so forth. And we'll use this because it gives us some interesting points that we can use to measure what we're looking at in the distance. We've got a railway track going off to infinity in this picture, with a series of telegraph poles equally spaced, also going off to infinity, and sleepers going off to infinity, and also fence posts. We'll be using the geometry of that and what we see as a measure of how telescopes work. And in this instance, you can see that if we use a telescope and see a bigger image, it will look precisely the same as this, but we'll be further down the railway track. Also, you'll notice that as you go into the distance there, the telegraph poles, the sleepers, and the fence posts get smaller, and they also get less bright. They get slightly dimmer. And a telescope, if it just magnifies, will give a dimmer image. But if you make the aperture bigger, in other words, make a bigger telescope, you get the brightness back. And telescopes are one area where size really does matter. Now, these nebulae were first seen by people using primitive telescopes, and these are some of the pictures that they saw. They're pretty vague, but I guess you can imagine that with small telescopes, not very well made, they were fairly difficult to imagine what you're seeing. Now, this is a modern picture, or two modern pictures of nebulae. The black and white one, I say modern, it's 1908, but it was a fairly large telescope that produced this. And the coloured picture there is one that was taken by an amateur astronomer, probably using equipment costing perhaps £1,500 to £2,000. Quite expensive, but if you're a dedicated amateur, that's the sort of money you might spend on it. And you can see that the results in that amateur image are just as good as the one from professionals in 1908 with a much bigger telescope. Now, the next step, of course, was to build bigger telescopes. That increased its magnification, and it increased the amount of light it could gather. And when you started to use these larger telescopes against the night sky, you started to see different things. You saw that nebulae themselves weren't constant; they varied. And if I go back to the picture of the railway line, we're now moving down that railway line. So we're seeing a similar picture, but we're seeing more detail in the distance. And one of the people that drove that revolution, of course, was William Herschel. And he built a 48-inch telescope, so they're getting big now. This is a drawing of it. And interestingly, it was located in Slough. I doubt whether you'd see much from Slough these days if you had a telescope that size there. I think it would be the night sky that you'd see would probably be illuminated by all the lights and a lot of the clouds and so on. And he generated the pictures on the right here of the images that he was seeing, and you can see we're starting to see some detail now. At the bottom, the two at the bottom are still very much cloud-like, whereas the ones at the top tending to be more structured. And you can see again, this is the amateur picture of the nebulae in Orion. And you can see that, again, there's a huge difference between the images quality that you've got with a small modern equipment compared to quite large ancient equipment. And if we go further on now, we see that this trend gets better. We've got Lord Rosse here, who built a 72-inch telescope, and there's actually a photograph of it here. And he started to resolve the images of galaxies much better, starting to see stars in them. The picture of the sketch at the top right here is one of Lord Rosse's sketches, and the diagram at the bottom is one that was produced by William Herschel. He actually started to understand galaxies, but he actually didn't publish or stick with his hypotheses. And what he did effectively was assume that we were at the center of a mass of stars, that the Milky Way represented that mass of stars, and he plotted effectively where the Milky Way was around us and ended up with the bottom picture. And you can see there's a section towards the right which shows sort of two limbs coming out of it. You'll look at that, we'll look at that in a later picture in a moment, and you'll perhaps see how it was generating something that was getting nearer the truth. Now, this is an interesting slide because it shows some of the very early images, the ones by Lord Rosse and a modern picture. And it compares the progression of the information that's seen. And you can see that the modern picture and those of Lord Rosse in the middle 1800s was fairly accurate. I ask you to remember that because we'll be seeing a similar picture later on covering the progression of infrared imaging of the deep universe, which will give you some indication of the progress that we are now making too. And these are some pictures of modern galaxies, modern pictures of galaxies. You can see on the left here, upper left, is a photograph of the Great Nebula in Andromeda. Below that is one of the first photographs that was taken of it. And then on the right, we have a whole cluster of modern images of galaxies. And you can see that they're very varied in shape and size and so forth. And if we look at this picture again, which is a modern picture, you can see a plot of, it says there's 65,000 galaxies there. I haven't counted the spots, I've no idea how you might do that. It doesn't look like 65,000 spots, but I don't really know how you stress that other than statistically. But this is a picture of the distribution of galaxies. Now, in the middle of that, you can see a sort of a grey line, and that is the area of the Milky Way, which effectively obscures all the galaxies beyond it. And I think you can see towards the top there, there's a slight branching of it, and that effectively shows what Herschel produced when he produced his image of what he suspected the local galaxy, although he didn't call it a galaxy, was at the time. Now, the next big step, of course, was to measure the distances to the galaxies. And this is where we need to look into parsecs, standard candles, and second variables. And if we go to our picture of the railway track, we're moving way down the railway track now. You can see, again, it looks very much the same, even though we're going down towards infinity on it. Now, hopefully, I've got a picture here, which I've superimposed a triangle on it. I shall use pointer on this and hopefully describe the angles involved. But if we look at that triangle, so one. If we look at the bottom of it, we've got a baseline here of a sleeper. We've got one side going down one railway line, and then we've got the other side going from this far distant point back to the other side of the sleeper. Although it doesn't look like a right angle triangle, obviously it is, because the angle at the lower left is a right angle. It's between the sleeper and the railway line. The angle at the lower right is slightly less than a right angle because you've got a misalignment between the hypotenuse of this yellow triangle and the railway line. And of course, by definition, that angle at the lower right between the hypotenuse and the railway line is the same as at the angle of the apex of the triangle. So although it's distorted, we've now got a right angle triangle there, which is very long, and it has at its apex a very small angle, the angle between the railway line and the hypotenuse. Now that angle is the parallax, and it's measured as 1 second of arc, and that triangle is defined, if you like, with a parallax of 1 second of arc, which is the same as the apex angle, and the baseline, the railway sleeper, is equal to the radius of the Earth's orbit. And that geometry of a right-angled triangle with the radius of an Earth's orbit and an apex angle of 1 second of arc, which, bear in mind, is 1/3600th of a degree, so it's quite tiny. And that's known as a parsec. It's an astronomical unit of measurement that effectively has been surveyed. And it's the actual distance is 30.9 trillion kilometers, or about 3.26 light years. But unfortunately, that wasn't good enough to measure the distances of most of the galaxies. Some of them are nearer and can be measured, but there had to be another technique for measuring the distances to the far galaxies. Now we come to standard candles, come back to the railway line. If you imagine there's a light on each of the telegraph poles there, and that light is constant, as you look down the telegraph poles, the ones in the distance get dimmer. Now, if you know that all those lights on the telegraph poles are the same, as they get dimmer, it's a function of their distance. So you can equate the distance with the actual brightness of those lamps. So if you can do the same with stars, then you can work out the distance that some object is away from you. I've thrown this one in before because this shows the techniques that we used before computers were readily available. And I believe these ladies here were calculating in the Harvard astronomy group, and they effectively carried out all the computations on astronomical measurements that were made before there were computers. Nowadays, all this can be done with a small piece of software and done very rapidly. But if we go back to what you got from certain stars, it was noted that some stars varied in their magnitude. They got brighter and dimmer. And because they could measure the distance to these stars, they could correlate the brightness to the distance. And they deduced that if you had a star that was oscillating with a certain change of brightness, if it was the same period of oscillation, it had the same basic brightness. It was effectively one of your lamps on the lamppost, on the telegraph poles. And from that, you could actually find the stars in our galaxy, which were quite close. You could use geometric means of measuring their distance, and then you could know their absolute brightness. And that group of these stars were in the constellation Cepheus, and they were the brightness and luminosity characteristics of these were worked out by a lady called Henrietta Leavitt. She looks rather like a classic school teacher, she probably was, but she actually worked out the luminosity distance relationship and the period for Cepheid variable stars. Now, once these were found in the galaxies, distant galaxies, you could then work out the actual distances by the luminosity of these stars. They were the standard candles that you could use to work out how far something was away. So the next step after this was, of course, to determine the width of the galaxies. To understand this, we need to look at spectroscopy and the Doppler effect. Sorry. I'm hoping that some of you are vaguely familiar with these things. We'll have a look at them and see if we can add some light to it. So if we look at spectroscopy, it's the display and analysis of the colours in light. And we need to look at a number of things there. We can go back originally to the work that was done by Newton when he split up light using a prism. He made a mistake originally by assuming that the dispersion and the refractive index of glass were the same. And because of that, he invented the reflecting telescope, which effectively is the basis of all the telescopes we use today, including the James Webb Telescope. But you can use pure spectra using lenses, prisms, and slit. And this was largely explored by a chap called Joseph Fraunhofer. And its application to astronomy was carried out by William Huggins. For a given material, the refraction is color dependent, and you see this effect if you look through a simple lens. A magnifying glass with a large magnification usually shows a slight rainbow around the edge of the image, especially if it's a bright white image. In a telescope where you don't want that effect, you use combinations of glasses to give you achromatic lenses which don't distort colors. And mirrors do the same. This is the sort of typical view that you get from a spectrum. You get these things coming from hot bodies. So the sun gives a spectrum. The filaments in the lights that are illuminating the stage give a spectrum. And if you get these pure spectrum, you see dark and light, bright lines in them. And this is to see what those lines are, we need to look at the Rutherford Bohr atom. Now, I'm hoping you at least know that one of the early and useful models of the atom is a universe type atom model where you've got the sun at the center, the nucleus in the case of the atom, and the planets going around it are replaced by electrons going around the sun. And when an atom absorbs a photon of light, one of those electrons jumps into a higher orbit. And when it emits a photon of light, one of the electrons jumps into a lower orbit. So they're giving up energy effectively, or absorbing energy. And on a spectrum, the dark lines show atoms absorbing photons, and the bright lines show atoms emitting photons. So they're called emission lines and absorption lines. And depending on the element, these lines form patterns along the spectrum. And this is a very complex spectrum with many of the elements shown. But we'll use a much simpler part of that, which looks at the effect of the lines on a simple spectrum, and is used to just define what you see in a star cluster. Now, we also need to look at the Doppler effect, because the Doppler effect is the change of frequency of a moving source. And you hopefully have seen examples of this with railway carriages going down railway lines with trumpeters blowing trumpet notes, and they change as you go past, as the train goes past you. So if the source is moving towards you, the frequency is higher, and as it goes away from you, the frequency goes down. And this applies to sound waves, light waves, and radio waves. And it's used in speed cameras and also in the examination of blood flow through the arteries of the body. And this effect is also seen in the spectra of distant stars and galaxies. And it's either redshift or blue shift, moving away from you or moving towards you. And so this slide shows you the effect of those absorption lines on the spectrum of different astronomical bodies. And you see here, if you compare the sun on your left here to a supercluster, which contains stars very similar to the sun, you get the same pattern of lines showing the elements are the same, but they're shifted against the background of color. And this movement is called the redshift. From that, you can actually work out how far away a thing is and how far away it's moving, how fast away from you it's moving. So these are those same spectra, two on their side. for a particular supercluster of galaxies, and with a velocity of nearly 1/10 the speed of light moving away from us, a distance of 1 billion years. Now, these measurements of both distance and movement were made by an astronomer called Edwin Hubble, and that's obviously the astronomer who the Hubble Space Telescope is named after. But he was doing this in, I think it was the 20s, using the Hooker telescope in America, and that was the largest at the time. The picture there of Edwin Hubble was the necessary pipe, and the picture of the Hooker telescope. And he plotted a graph which shows the distance to the galaxy, and the speed is moving away from us. And you can see from the bottom the distances involved. That's 2 times 10 to the 6 parsecs. So we looked at the parsec earlier and saw how large it was. And this explains, of course, why you couldn't use a surveying geometric technique to measure the distances. You had to use these Cepheid variables. And then you've got the velocity of motion on the side there. And this slope of those plotted away showed the fact that the universe was expanding. And so that obviously led to the 2 theories that were developed: the steady state of the Big Bang to show that the universe was expanding, and to fit theory, if you like, to measurement. But interestingly, at the bottom there, you'll see that because there's a finite speed of light, it meant that the furthest, most redshifted galaxies were the oldest, and also they were the smallest, faintest in any image. So what that meant was that you needed to look at infrared astronomy. In other words, you needed to look at light beyond the normal visible wavelengths. And so we need to look here to understand that, these points: the electromagnetic spectrum, the atmospheric transmission of electromagnetic radiation, the abilities and limitations of the human eye, photodetectors and light integration, force color imagery, and Narcissus. And I'm sorry if this is a great load of data, but hopefully we can step through this and gain some understanding. So if we start off by looking at the electromagnetic spectrum, you see here at the top of the white block of writing, we're looking at different electromagnetic waves going from gamma waves through X-ray, ultraviolet, through the visible, infrared, microwave, and radio. And from one end of the gamma ray, you have the shortest wavelength, highest frequency, and the other end you have the longest wavelength, lowest frequency. So what this means, of course, is if you plot it normally with, say, the smallest element to your left, you end up going from gamma rays up towards radio waves as the wavelengths get longer. But of course, the actual frequency is reversed. So you've got the highest frequency to your left and the longest frequency to your right. And if you'll notice there, the visible section, which is quite a very narrow portion of it, the violet and blue end of it is to your right, sorry, to your left, and the red end is to your right. If you see other pictures, which I have to show you, they will be the other way around. And so, because they're plotted with the shorter wavelengths to one side, sorry, the longer wavelengths to one side, but the higher frequency, it then gets reversed. And you can tell that if you look at this by noting that the rainbow in the middle of it, which is our visible window, has the colors reversed. The red is now to the left, and the blue purple is to the right. I'm going to take the photo. Excuse me a moment. Now, you can see from that the on this curve in the middle, you've got a shaded area, a rather raggedy shape, and that shows the transmission of the wavelengths or the radiation through the atmosphere. In fact, it shows the absorption rather than the transmission, and you see that there's a nice big gap where visible light is, but if red, you see big chunks of it that are filled up by absorption by the atmosphere. And this is shown again in this slide where you see that the visible light is in a nice window, whereas the infrared radiation, which is going off to your right, is actually obscured in many areas by absorption of the atmosphere. And this is yet another more detailed picture of that. Now, this is effectively what the atmosphere does to that radiation. And we also need to see what the detectors that we use to view that radiation, what effect that has on it. So if we look first of all at the human eye, and bear in mind that all the earlier observations were carried out using the eye, we've got effectively a little camera here with the lens at the beginning of it, at the front of it, and a retina at the back, which is composed of an outer part which has fairly sensitive photodetectors, and the macula, which gives us our detail and color. And if we look at the cells that make that up, we've got the rod cells around the periphery of the eye, and the cone cells in the macula, or the detailed center of the eye. And these pick up dim light around the outside and detail and color around the inside, the cones on the macula. And interestingly, we have a very good, most of our sensors that we have, including the eye, are very, very good in performance. But what they don't do is they don't integrate the color, the light. Whereas the photodetectors that are used both in cameras and in the James Webb Telescope can integrate the color of the light. But the human eye is very good at pointing to the object that you want to see in detail. Sorry, I've gone the wrong way there. That's it. So when you see something in the peripheral vision, you just see a glimpse of it with no detail, and your eye is very good at swinging to look at that thing. So what it does, it adjusts its pointing to put the macula, the detailed part of the eye, onto the object that is called to vision in the periphery of the eye. So that pointing is something that's very important, and we'll see later on what impact it has. So if we now look at the response of the eye and film in this case, we can see the colours on the left there of the response of the various cones and rods in the human eye, and on the right we've got a picture showing the response of basically the eye at the top, and then underneath that the three lower dotted lines on the curves on that picture show you the response of different films, photographic films, and you can see that the basic simple photographic emulsion that was first developed tends to work very well in the blue and ultraviolet part of it, and it took a while for a orthochromatic film to be generated, and then finally a panchromatic film which had a good response where the eye was, and also in the ultraviolet and short wavelength part of it. And this is one of the reasons why if you had an old-fashioned film camera, that it was always good to use a UV filter if you were taking pictures of large scenes, because that filtered out the hump of the panchromatic film and made it respond very much better and much more similar to the eye. Now, one interesting point about film is that you can actually integrate an image onto film. If you give a very long exposure, a very faint image will gradually build up. The eye doesn't do that. And so the idea of concentrating an image for a long period of time to gather more detail is something that you could only do with photographic film and other forms of light detector. So if we now look at other forms of light detector, we have a picture here, which at the extreme left shows the little window for the visible light, and then it shows the response of a whole series of photodetectors that can be used, including various chemistries of different photodetectors made from alloys and semiconductor junctions. And we've got a whole range of them and their different responses. And you can see that since the plot of this curve goes towards the right, and that corresponds to increasing wavelengths. We've got very large areas of there which we can detect using photodetectors, but which we can't see with the naked eye. And so if we go back to the this next one here, we've got effectively arrays of those. Sorry, I've gone back to the wrong one here. That's the one I want. My apologies. You can see we've got arrays here of those detectors, and in fact, on the right there is an array of detectors used in the James Webb Space Telescope, and it's actually used to point the telescope in the right direction. I mentioned to you earlier that the eye is not very good at integrating light, but it's very good at pointing directly at the object you want to see. Well, in a telescope that you're looking at very faint optical images from far away in space, you need to be able to both point it very accurately so that you can allow the image to fall on the detector for a very long period of time and build up an image. And on the right there is a guidance sensor of the James Webb Space Telescope. And effectively, what you do ultimately is you form an image of the stars around the object you're looking at, and you make sure that that image remains stationary in the telescope. And that means then the telescope can look at something for long periods of time and build up an image from very faint inputs.
I think it's doing this.
I think it is, yeah. Yes, can we do that?
Has the internet gone down?
It seems to have done, yeah. Someone here.
Are we back?
We're back to the presentation, but
Yes.
not for online.
Yes, so we'll run,
Continue.
Okay.
and we're recording, so we'll send the recording to those people who are attending remotely.
So what do yes, we've got to looking at these redder and fainter images from the far depths of the universe. So the one point that I wanted to bring out now was another one of the optical phenomenon that had to be taken into account with infrared telescopes. This is an optical phenomenon known as narcissus. And this is one of the reasons why to get very, very good infrared images on the imaging systems, you have to cool the detectors and the camera itself. Because every object emits radiation. We're all warm and we're all emitting radiation because of that. And depending on the object's temperature, it depends on the radiation that you emit. So if you've got an incandescent filament, such as in a light bulb, then that emits radiation that's effectively the same as the visual radiation that we're looking at. So if you imagine trying to make a camera that was made out of metal that was white hot, it couldn't operate as a camera at all. And unfortunately, when you look at infrared radiation, the temperature at which you start emitting radiation that can blur your image gets lower and lower. So you need to cool both the detectors and the structure of the camera to stop that effect happening. Now, some of the early infrared telescopes were cooled by nitrogen ice, solid nitrogen that was sent up with them, and that evaporated off and cooled the detectors down. Of course, they had a limited life. And later ones again used liquid helium, which gave you a lower temperature, but again was a finite source of fluid. We'll see eventually what the James Webb Space Telescope does to overcome this. Also, of course, the Earth, the Moon, and the Sun also give off lots of radiation. The Sun, obviously, because you can feel that. In fact, you can get burnt by the infrared radiation in the Sun. But that from the Earth and the Moon is sufficiently strong to be a bright image as far as the infrared telescope is concerned. So you don't really want to be able to see either the Earth or the Moon in your telescope's field of view. So one way to do that, of course, is to put the telescope in space, and that gets rid of the first problem, which is the absorption of radiation by the atmosphere. It starts to get you in a situation where you can see much more of the coldness of space with infrared images in it. And one of the first large telescopes was mounted in a Boeing 747, and you can see it here. And that effectively got over the absorption of the atmosphere by flying very high up, and was able to view images from high up. The other way around this, of course, is to use a sounding rocket. The early ones were sent up in sounding rockets, but they had a very short period of time in space as they arched over the top of their trajectory. And you had problems at pointing the telescope and also integrating the light from the telescope. So really, you started to contemplate putting infrared telescopes in Earth orbit. And this shows that some of the precursors to the James Webb Space Telescopes, and that gave better seeing, of course, but involves the complications of rocket and satellite technology. If we look at some of the precursor telescopes, you can see here the various apertures of each of them. The N figures in the block there show you the aperture of the telescope, how big the diameter is. And you can see in the middle of that the Hubble Telescope is quite a large one, 2.4 meters in diameter. And then the other ones are quite small. And this is because, of course, you have to send them in a rocket into orbit. So it couldn't be a very large aperture telescope. But then you see at the bottom there is Herschel, which again is an infrared telescope, one of the precursors to Hubble, to James Webb Space Telescope, which didn't receive quite as much publicity, but it was 3.5 meters in diameter. It was a solid mirror, and it was sent up on a large rocket, the Ariane 5. But it also went into orbit, and what was known as a halo or isogas orbit, which we'll come to later, about Lagrangian point 2. Now, of course, sending telescopes into space involves all the complications of putting it in orbit and how you point it and so on and so forth, how you cool it. We could spend a long time going into the problems of launching satellites and rockets, but we don't need to do that. We'll just look at the ones that that gave information prior to the James Webb. And we've got IRIS, just over half a meter in aperture, launched in 1983, and 100 microns wavelength to the infrared, so quite deep infrared. We've got the Hubble Space Telescope with 2.4 meters in aperture, large, and launched in 1990. But I put a question mark by it, also because it had to be rectified. They had problems. I think it was about 95 when it started getting the infrared images, and that was quite a low frequency infrared, quite a low wavelength, 1.7 microns, but it gave a lot of useful information. And now the Spitzer Space Telescope, again, just about coming up to a meter in aperture in 2003, that looked at 100 microns, 160 microns, which is very long wavelengths. And then Herschel was the space telescope, which is one of the most recent ones prior to James Webb, which was launched in 2009, 3.5 meters in aperture with a single slab mirror, and looking at 670 microns, which is very deep infrared. And then finally, you come to the James Webb Space Telescope, which is, in terms of aperture, it's very large, 6.4 meters aperture, and launched in 2022, and at 28.3 microns. So not quite as deep into the infrared as some of the other telescopes, but deep enough to give information. And we can start looking at some of the comparisons of these. This is a picture which shows a false image composite picture, and it shows you the results obtained from the Spitzer Space Telescope using visible, medium, and long wave infrared, and there down the side there on the right, the visible, medium, and long range infrared. And they're composed into the large part of the image on the left to give you this false image, which shows you information which you can't obviously see, but is there hidden in the data. And now we go back to this picture, and if you remember the picture at the beginning, near the beginning, which showed you the progression of images from bigger and bigger telescopes in the visible light, this is the progression of detail that we get as we go through different telescopes in the infrared. And you've got from the extreme left, the WISE telescope very early on. Then you've got the Spitzer telescope. And finally, you've got the James Webb telescope. And you can see that the progression that you've got there is almost as good as the progression you had from the early telescopes going to larger apertures, and then finally the biggest ones. And so here we go back to the picture that was shown at the beginning of the Hubble telescope. And you can see again that we've got here the various small galaxies, and we can see their redshift and their distance from that. And we can look at that in the next image, which shows you 3 pictures of the same area taken with different telescopes with different capabilities, differences in aperture and differences in wavelength. The larger image is from the visible deep field image of the Hubble. The one at the top on the top right is the Hubble visible image. The middle of on the right is the Hubble image with its infrared camera, and you can see in the circle that you're beginning to see a red spot emerge in the middle. Below that is one that was taken by the Spitzer Space Telescope, which is deep in the infrared, and you've got a very large image there in red, but not as good in resolution because it's a much smaller aperture. So you've got a failing of resolution, but you've got more information in the depth of the frequency that you're looking at. Now, I mentioned earlier that the Herschel Space Telescope didn't orbit Earth, but it orbited around Lagrangian point 2. And this is the final bit of confusion that we'll cover. If we look at Lagrangian points, we need to consider how an ordinary satellite goes around the Earth. And what it does effectively is it balances the forces of its motion in going in a circle, centrifugal forces, if you like, against the gravitational pull of the Earth. Now, there are other areas where you end up with a similar effect, where the gravitational pull of the bodies involved balance each other out. And these are called Lagrangian point after, I think it's Jean-Louis Lagrange, one of the famous French mathematicians. And there are 5 of these. There's obviously one between the Earth and the Sun, that's L1. There's one on the opposite side of that, complementary one at L2. There is one also on the other side of the Sun called L3. And there are 2 points where the Sun and the Earth balance out at L5 and L4. And those ones are where you tend to put sun observing satellites like SOHO. It's perhaps worth looking at these in terms of how they appear in terms of gravitational gradient, because we've got a situation here where you're not balancing the forces against gravity as such. You're going around a point which has 0 gravitational gradient. And so you can see on this slide those Lagrangian points, which show effectively points where gravity is 0, even though there's nothing there. The gravity balances out. If you look around the Earth and look at where the Moon is, and that, if you like, analogously is where satellites will be, you've got the well of the gravity of the Earth being balanced by the motion of the satellite and the Moon. But at the points at L1 and L2, there's no gravity. So you've effectively got a virtual body which you can orbit around without using much energy. And this slide shows you a picture of the James Webb Space Telescope orbit around its Lagrangian point. Now, it gives you some information about the axes and so on, but what essentially it means is if we go back to the earlier slide, you've got if you imagine the axis going from the Sun through the Earth going to L2, you're actually orbiting around that, rather like a toffee apple, if you like, on the end of a stalk, and the stalk is the axis, the toffee apple is where you're going around. And the reason they're called lysogas figures, and again, I don't need to decide here, but I don't know whether any of you have seen lysogas figures on an oscilloscope. And what you have here is effectively 2 axes causing the motion of the oscilloscope to give you these figures. Now, if you look at the middle top of the data in the white block, you've got a circle. So that represents, if you like, a standard orbit. And that's the sort of orbit that you put around the Earth. And on either side of it, you've got ellipses, and they're the sort of things you can put around the Earth too. But because this is going around a Lagrangian point where there's no body, it's actually a virtual point in space, if you like. You can also do these other shapes, which you can do on an oscilloscope tube. So if you look at the second line down in the middle, you've got a figure of 8. And theoretically, you could orbit something in that shape around the Lagrangian point. But you don't actually want to do that. It's just a point why it's called a lysogas orbit. So I think actually at that point, we've covered all the aspects that I mentioned in the original list. And we can get finally to the James Webb Space Telescope. Right, so what we've got here is a picture of Mr. Webb, James Webb. And funnily enough, he wasn't an astronomer. He was an administrator, really, a manager. But he actually was managing NASA. And even before Hubble telescope was launched, he realized that there would need to be something beyond that. And he organized all the early investigations into what you needed to launch. And effectively, he honed in on the fact that you needed a far distant, a far infrared telescope to look into the deepest parts of space. And it needed to be a very large aperture infrared telescope. So it was named after him. And obviously there's a picture here of an image of it, which actually is, again, wrong. And we'll see why in a moment that it's wrong. But we'll look first of all at the aspects of this. You had to have a large aperture of the telescope. You had to have reflecting objects. The only way you could do that was with the segmented folding mirror, so that you could fold it into the confines of a launch rocket. It had to be above the atmosphere, so it had to be sent into space. It had to have a highly accurate stabilization and pointing system, so that you could stare at something for a very long period of time and integrate the very faint light waves coming from it. It had to see in very low frequency infrared, very long wavelengths. It had to have a pool detector. And also on top of that, it had to have the instrument behind the sunshade so you couldn't see the sun. And of course, you didn't want to see the Earth or the Moon either. So they had to be outside the field of view and behind the sunshade. This is one of the reasons why it was placed at the Lagrangian point L2. That, of course, meant it was in a halo or Wasserdash orbit around that virtual point at the Lagrangian point 2. And the segmented mirror had to be erected in orbit. Obviously, it had to take off with it folded and had to be erected in orbit. And the orbit being, of course, around that point. And the sunshade too had to be erected in orbit. And furthermore, there was no chance of a rescue mission. So if they got it wrong, they couldn't go back up there and put some form of correction in it. So that was effectively the James Webb Telescope. And now we finally come to some images. So the first one here is a picture of the Ariane 5 taking off. And we have next to it a picture of the actual telescope in its folded form. You can see the elements of the segmented mirror stacked one upon the other, and also rather curled up in there are the elements of the sunshade. We go to this slide, you can see how it sits inside the rocket. You've got the telescope in a large aerodynamic fairing at the top, folded up. It sits upon the top of a second liquid propellant stage, which sits on the main sustainer liquid propellant stage underneath it, with two boosters strapped on the side, solid propellant boosters to lift it up through the early parts of the atmosphere. And this image shows you actually the James Webb Telescope as it would normally be seen, where the actual telescope is behind the sunshade. You have the illumination on the sunshade side, the telescope sitting in its shadow. And of course, if that was actually a true image of the telescope, the brightness of the reflected light from the sunshade means you wouldn't be able to see the telescope itself. But it's a better artistic image than most of the ones that you see, which effectively show you the telescope on the sun side with shadows and everything on it. And now we can look at the images that some of the images that have been detected, and these are by no means the latest ones, which if you go onto the web, you can see a new one almost every day. This is a group known as Stefan's Quintet, and an amateur can see this in a fairly modest telescope. Nothing like the detail here, but there's sort of four or five vague patches of light. Here you see quite considerable detail with lots of other galaxies in the background, which you'd never see in an amateur telescope. But not only can the James Webb Telescope look at distant galaxies in the deep reaches of space, it can use the actual infrared imagery to look at planets in a different way. And this is Jupiter looked at in infrared. And because it's in infrared, you're starting to look down through the atmosphere. You can see a different layer in the atmosphere. So you're learning the difference between the planet as it is, and the planet in optical images, and the planet in the infrared. And you can see that there are vague marks around the planet. They're rather like the rings of Saturn, and in fact they are rings of dust. And you can see one of the satellites of Jupiter over to the left of the image with a ring of dust showing it on there. And also, I believe you can see the effects of aurora or storms. I'm not sure which they are, but they illuminate the north and south poles of the planet. And again, I think this is Neptune, and again you can see the satellites of Neptune going around in the rings of dust. And I believe there are again lightning or storms of lightning in the atmosphere of Neptune, which you can see through looking at it in the infrared. So although the James Webb Telescope gives us all this information about deep space and deep time, you can use it for examining a lot of the planets in our solar system and getting more detail about them. And then finally, we come to this image, which is one from James Webb, analogous to the one that we saw at the beginning of Hubble. And to give you some information about this, first of all, we've got lensing effects. Sorry, the which you see on some of the galaxies, they're twisted into sort of arc-like shapes. And this is an effect caused by bending of the light by gravity around other galaxies which that light is passing past. An Einstein effect that's only really been visible in these very, very powerful telescopes. Also, interestingly, one final statistic, that this effectively is the size that you would see if you held up a grain of sand at arm's length. And you can imagine that if that information is that small a part of the sky, how many of those that you could see all around you, and the sort of data that's coming back, it's the sort of information that will probably never be able to get through in ever. That I'm afraid ends my waffle. Thank you very much. If you've got any questions, I'd be happy to attempt to answer them.
We do have question time, and Gary's going to bring around the microphone to anyone who'd like to ask a question. Yes.
Some details about different telescopes and what are the ways of calculating?
Sorry, you can't hear the question.
The budgets for the various telescopes.
Right, I'm not going to be very good here because I don't. Obviously, the very early telescopes that you saw from people like Herschel and Ross, they were fairly rich men that were effectively making their own telescopes, so the budgets were a bit difficult to compare, and I can't really give you much information about that. Suffice to say that they were pushing the technologies at the time, and they were casting their own mirrors. They were doing everything as an amateur would, but on a large scale, and they were able to do that because they were fairly well off. They probably had lots of servants to operate all their equipment and get it to work. When we come to more modern telescopes, I believe, I know for a fact that the IRAS and Spitzer telescopes were roughly between 1 and 2 billion pounds each. I think pounds or euros, very similar. I'm not sure about Hubble. I think that was quite a bit more expensive now. Perhaps in the tens of billion. And it depends also whether you amortize the cost of the shuttle as part of the telescope cost. And I believe that that James Webb was, I think, in the 10 to 20 billion pound bracket. Again, I'm not completely sure, I'm afraid, but you can probably get that information on the web quite easily. Sorry, that's not a good answer for you.
Do you hear me?
So,
Thank you very much. Fascinating presentation and so much detail. Most grateful to you. I say my telescope cost about £1,200. So different sort of dimension of the telescope you've been talking about. Very basic and obvious question. Difference between a nebula and a galaxy.
well, I think nebula were originally named after clouds, and they were fuzzy. So they didn't really have any distinguishing marks other than they were rather like clouds. But when you could see a galaxy, you could see more structure, and eventually you started to be able to resolve stars in a galaxy. And that was the key, because once you could see stars in a galaxy, if you saw any of them varying in brightness at a certain speed, that was a Cepheid variable, and you knew how bright it was. So then that meant you could actually tell the distance by how dim it was compared to one of the nearby.
So we, the Milky Way, are a galaxy.
Indeed we are, yes. And effectively you could say that Herschel was correct, but he didn't have his conviction to carry what his theory was to actually saying, we live in a galaxy and this is it, and this is how it's structured. If he'd done that, he would have actually effectively defined galaxies a long time before anybody else.
Yeah.
I didn't follow what you meant by integrated light,
And
as
this is,
opposed to what sort of light.
okay, this is the fact that with a film or a photo detector, you can't do this with the eye. If you leave it pointing at a very weak source of light for a long period of time and you don't move it, it gradually builds up an image. It absorbs all of the photons of light progressively and adds them together. You can't do that with the eye. If you look at a very dim light that you can see, and you look at it for a long period of time, actually you end up not seeing it because the eye likes a change. So the way to see a very faint object in the periphery of the eye, in the retina, is to actually move your eye and you see it move, and that will gain your attention. If you see it stationary, you actually don't see it. Whereas, as I say, a photodetector can look at something for a long period of time and build up a better picture. So some of the early photographic pictures that were taken on photographic film very early on they were pointing at the sky for hours at a time, building up an image over that time.
Thank you. You may have dealt with this, and I didn't quite follow it possibly, but what is the advantage of false colour enhancement of images?
Yeah, essentially, when you see an infrared image, you're looking at something which you can't see with the eye. So you can only see it by substituting another colour. And obviously you can either compress that image or you can expand it. So if you have a range of frequencies in the infrared, you can either fit the visible spectrum to them by expanding them, or you can actually take bits of it and colour those separately. So that means that when you see an image from Hubble or James Webb here, if you looked at that, if you could imagine seeing that with the naked eye by building a sufficiently large optical telescope, you couldn't see it with the naked eye. You have to use a detector that looks beyond the wavelength that the eye can see, and then you have to substitute that image with another colour so you can visualize it. Does that make sense?
Are there any questions online?
Not when I looked a minute ago. Let me just double check now.
This is just a simple little question. When the comet was overhead a couple of years ago, we went out to look for it. And people with telescopes couldn't find it to begin with, so they started looking elsewhere. And I was determined to find it with my naked eye, which I did, but only after my eye passed it. Was that what you were saying, the integrated light?
Yes, indeed.
So I wondered if it was to do with rods and cones and only seeing.
That's right. The periphery of the eye, the retina, which I think is cones. No, they're the rods. Sorry, the periphery is the rods. They pick up faint light, but not in detail, not in colour. They pick up all light, but you only see it usually as a sort of a greeny colour in the background. And you see that because it's moving generally. If you're looking at an amateur telescope where you've got a very faint object, the way to see it is not to look directly at it, but to look to one side and possibly wobble the telescope slightly, and you see it moving. Once you stop moving it, you can't see it because the eye also uses movement as well as detection. But it's not very good at, if you stare at that for a long time, it's not very good at making it brighter. It will just disappear. Whereas if you take a photograph and point it at the same dim object and leave it there for a very long period of time exposing, it will build up a brighter and brighter picture. And that's what happens when you integrate the light in a photodetector or a film. And that's the sort of technology that you're using in these telescopes. You're looking at a frequency that you can't see, which is too dim to see, but you're using an instrument which can detect that frequency and can look at that frequency long enough for it to build up an image. And then because that image is then a signal, if you like, and you can then say, well, we'll display that signal as a colour, and then you can see it with your eye. Does that make sense?
Yeah, the telescope, when I spotted it a couple of times, as my eye moved, that was again. Then I looked back and it wasn't there anymore.
Right.
But then I had a chance in it. And then the chaps, the telescopes, then they looked at it, and then they found it, and then we could actually see it through their
because
equipment.
the telescope has got a bigger aperture, so it's gathering more and it's concentrating it down and making it visible to you, because it's making it bright enough for your macula to see it, which is the detailed coloured parts of it, of your eye, and you can then see the image of it. Comets are quite difficult things to see actually, because if you've got an amateur telescope, which is quite a modest aperture, a comet is not a particularly interesting thing to see very often, because you just see a bright area of fuzziness surrounded by a larger area of slightly less fuzziness. If you're lucky, you get two tails and you can see the tails. And if it's a complex comet, such as the one that crashed into Jupiter in about 1995, was it, sometime like that, you can sometimes see the bits of it. And in fact, the one that collided with Jupiter, you can actually see through a middle range amateur telescope, you can see the impact marks on the surface of the planet. But again, that's because you're looking at something with a very large aperture in the visible, so you can see it with the eye, and you're looking at something which has got sufficient brightness to illuminate the macula of the eye, and you see the detail.
I recognise the comet because it looked like a picture of Halley's comet on the Valiant tapestry.
Right. Well, hopefully not too much like that. So that's a rather idealistic.
That was my evidence.
Yes, okay, sure, yeah.
One more
Yes.
question.
One more question. Yeah.
So,
Thank you for your explanation on the word integrate. So am I right in believing that you're using the word integrate in the mathematical sense of summation?
yes, that's correct. Yeah.
Part B of the question. One of the characteristics of the next generation of telescope that the engineers are working on now to put into space in 5, 10, 15 years' time.
I think it depends what you want to do. If you're wanting to look into deep space, where you want to see further and further away and try and look back in time, and that's one of the objectives of these infrared telescopes, because we want to try and look as close as you can as to the Big Bang, if you like, then you need to make a bigger aperture so you can see fainter galaxies, and you need to look further down the infrared spectrum. You need to look at longer wavelengths, lower frequency ones, that show you effectively the image that you will get from something that is moving away from you very, very fast, and a long way away, and it's very faint and small. Obviously, there's a limit there, because as you start to get close to the speed of light, you can't see it anyway. It goes out of the sort of, it becomes radio waves, if you like, and then the radio astronomers will say, well, we can do that, but we can't do it as an image. They haven't got radio telescopes that can produce the sort of resolution that you get with optical meaning infrared telescopes. And the other thing, of course, you can do is you can start looking at different wavelengths, looking at the planets, and you start seeing different things on the planets. So, for instance, we look at the sun, and effectively, because we're looking in the visible, we see the outer part of it, which I think is the chromosphere or the photosphere, I can't remember. But you see the bright bit on the outside. You can only see further down into it if you look at it through very, very narrow filters that cut out all of the visible light, or the high frequency visible light, and take you down into the red part of it. And you've got to look at it in hydrogen alpha, and there's a calcium wavelength that you can look at it in. And then you see different parts of the sun's surface. And obviously you've then got the other effect on the sun, where if you block out the brilliant central part of the sun with either the moon when you see a solar eclipse, or with a mask when you're using a solar telescope, you can then see the prominences around the outside of the sun. Oh yes.
It just remains for me to thank John enormously for such an interesting and, well, I'm just trying to find the word. It's so well researched, so knowledgeable, and it didn't stop with the talk. It carried on through all the questions as well. He wasn't flummoxed by anything. So,
You tried hard enough.
so, John, thank you very much for entertaining us and instructing us so well.
Thank you. Thank you for coming along and having a ramble at you. Thanks a lot. Cheers.
I'm editing.